Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. May I ask you to turn off your cell phone because the cell phone will interfere with the microphone when the question is being asked. Thank you. It's my pleasure to introduce Mihai Christodorescu. I'm still practicing pronouncing his last name. Mihai is a PhD candidate from University of Wisconsin, from the computer science department. He works with Professor Samas Jha. And he's going to tell us about his dissertation work on behavior-based malware detection.
Thank you for the introduction, and thank you all for being here this morning. So, as the title suggests, I'm going to talk about the core part of my dissertation, a new behavior-based approach to malware detection. At the end, I'm also going to mention some other work I've done, but the talk today is going to be about malware detection. So let me first start with the very basic. What is malware? And there are many definitions. There are many kinds of malware. Depending who you ask, you'll get a different definition. In recent years, we've seen combinations of behaviors. So the line between the classic types of malware is being blurred. You see viruses that also act as worms and Trojans and so on. And the threat is being increasing in the last couple of years. In January, Vint Cerf was mentioning that he believes that up to 100 million machines might be infected at that point. To give you a kind of idea, if you, as a rough estimate, this means that about 1 in 10, or between 1 in 10 and 1 in 6 machines are infected across the whole internet. So why is this trend right now? Why do we see this nowadays? Basically, it comes down to money. You can make money from infected machines through online fraud, by stealing information from those machines, by sending spam from those machines, and so on. As a quick data point, in January, a Swedish bank lost $1.5 million. Basically, over one weekend, customers of the bank were spammed particular Trojans. Whoever clicked on a Trojan and ran it, basically their interactions with the bank were monitored, their username and password got stolen, and then the attackers used those credentials to log into their bank account, transfer money out of their bank accounts into some banks in the US, and from the US into some banks in Russia. And from that point on, the money was gone. They couldn't retrieve it. So the bank had to cover these losses. So really, this has a big impact beyond just spamming that you see every day in the financial markets. And in many cases, you cannot recover these losses easily. So what's been happening really in the last 10 or 15 years is that the threat has changed. Because of money, because of many other reasons, we're moving away from a model where people write malware for fun. It's not just for bragging rights or for being able to claim that you infected 10 million machines. Rather, nowadays, malware writers work in organized teams. The software is developed professionally. They actually apply good software engineering techniques. It's modular. It's easy to update and distribute. And really, this takes this peaks in what you see now with botnets. These are networks of infected machines, all of them under control of one attacker. Think of what you can do if you control 10,000 machines across the whole internet. Well, you could launch denial of service attacks. You can set up any kind of service you want on them. Think what you could do if you have 1 million machines on those. So from a point of view of somebody who wants to actually commit fraud online, or let's say phishing fraud specifically, you really need a couple of infrastructure pieces. First, you need to email a list of possible victims. Then you're going to create an email message that has to look like it comes from a real bank. You need to distribute this message, and for this you'll use infected machines as spam distribution points. You need to host the website that collects the credentials, basically the phishing website. And finally, with all these credentials that you collect, you need somebody else to transfer the money into these bank accounts. And for this, you usually use a mule that will get a cut of the transfer. If you actually see those spams that says "Help us transfer money to our country for this so and so," some of them are actually true. You may actually make money in that process. Of course, it's all legal, so you may end up going to jail. But it's that part, the last step is actually not always a scam. We'll give you another data point. These botnets are traded online per 1,000 machines, and you can buy them for fairly cheap, $300 per botnet hour. It's basically computation time distributed out there, and the price varies based on the location of the botnet. So university machines are cheaper. They're easier to break into, easier to get, less monitoring. If you want machines part of, let's say, the Department of Defense, they'll cost you a bit more. I'm not sure what the price is for Microsoft botnets. I'm not sure if there are Microsoft botnets. But the key point is that there is this malware economy that's set up. You have people that write malware that sell it to people who actually will distribute the malware. In turn, will make money that will basically fuel this cycle. More development, more money being pumped into the malware economy. So the question is, how can you get away with creating so much malware? Fundamentally, it's because the detection technology hasn't changed in 20 years. At the core, virus detectors nowadays use byte signatures. This is basically a byte sequence. You check a file against this byte sequence. If it matches, the file is malicious. So by using byte sequences that describe malicious code, non-malicious code, you can detect the same copy of the malicious code when it arrives in your system. In the end, this means that you're building a huge database of signatures that you check your malware against. And this database has to be continually updated, and people recommend daily updates or even hourly updates. What malware writers can do to avoid detection, they can simply generate a new variant. If you think of taking, let's say, a program written in a high-level language, C or C++ or Visual Basic, and modifying it a bit such that its a binary version no longer matches the signature, it's very simple. Sometimes even simple compiler switches will change the format, the file of the format on disk. So it's really easy to generate many variants. In many cases, we see hundreds of variants per day, usually at around holidays and so on, when you see all those postcards flying around. So if you combine that to the fact that people are interested in writing malware because of money, and the fact that it's easy to bypass detection, basically the trend is that malware writers are getting smarter while detection technology hasn't moved on for years. So what can we do? Well, I looked at numbers. If you look at the last couple years of new malware, notice that the y-axis is a log scale, which shows that the number of malware per year is almost exponential and growing. There is no slowing down trend. But if you group this malware into families, and by families I mean you group malware that have a common code base. If you analyze them, if you analyze two pieces of malware, they appear to have been compiled from the same source code, then the numbers paint a completely different picture. The number of families over the last couple of years has been stable or slowly decreasing. And certainly, there are certainly fewer families than malware variants. We're talking about here 2 orders of magnitude difference, from 80,000 to 200 or 300 families.
Your definition of malware is byte sequence. What's the red? What are the things on the red bar?
The red bars are distinct malware instances, so distinct files.
Distinct. So it's just a set of bytes. Okay.
Just a set of bytes.
Got
Let me just say this before I go on. The definition of a malware family is very fuzzy. Basically, I'm using the numbers from the antivirus companies, and the definition of family varies from virus company to virus company. But the average, the numbers are about right in several hundred families, while we have tens of thousands of variants. Yes.
How much confidence do you have in your characterization that existing antivirus products still use only signatures, and why?
So this conclusion is based on the fact that they're easy to bypass. And this is not just what I noticed in the wild from the viruses that are out there, but also in experiments where through simple obfuscation you can bypass them. If they do more complex analysis, it doesn't show. In the end, it doesn't matter.
Yeah.
Oh.
Would a single polymorphic or metamorphic worm cause that red bar to go to millions? I mean, it looks from the script that there aren't any, serious polymorphic malware.
That's true, and a polymorphic worm, yes, it would probably, can have millions of variants. I think what's counted here is the number of variants that are actually seen in the wild. So if the problem of most advanced worms that use polymorphism and metamorphism is that the obfuscation or the implementation is not very good. So after a couple of generations, the new code fails. So then it's not considered malicious anymore. It's hard to write self-contained, binary analysis that can propagate and be in a compact implementation.
Or is it more likely that they just don't need to get it right since the virus detectors don't catch them with the simple things?
I think it's a combination of both. They only need to evade detection. They don't really need to break the whole system. Just enough to infect a couple of more machines to get them part of a botnet and move on.
So does this indicate there's a rise in the polymorphic and metamorphic viruses?
I can say for sure there are many definitions of polymorphism and metamorphism. So on one side you have viruses that will mutate themselves as they propagate. And we don't see too many of those nowadays. At least I haven't seen any that appear on the charts. But what it is more visible is I guess what's called server-side polymorphism, where the obfuscation happens before the first initial distribution. So somebody has source code initially, generates lots of variants locally, and then distributes them. The key thing is that they're all generated from the same source code. So obviously we like to focus on variants, focus on families, not on variants, because it's easier to trace the lower curve instead of the high-end curve. But actually we can do something even better, because families are not very well defined. We can focus on what I call behaviors. And to just give you an intuition right now, behavior is high-level operations such as self-propagation via email or opening a backdoor in the system. So, what I'm going to do in the rest of the talk basically show how to map these English descriptions of behavior into something formal that we can actually detect. And instead of focusing on families, we can look at behaviors as being basically a cross-cutting piece of functionality that is common to many families. There are many malware families that are mass-mailing worms. Each member of the family spreads through email, but the families are considered distinct because the code bases appear distinct. So in my work, I looked at behavior and defining them formally. And for this, I defined something called malspec, or a specification of malicious behavior. In the test, I'll show you how one malspec can catch tens or even hundreds of variants. And as the implementation improves, I hope it will do even better. I'll show you how to do efficient detection. In general, the problem is if you move from a simple representation just byte sequences to something more complex, the detection becomes more complex and slower. And making it faster or fast enough is a definite goal in this case. Otherwise, people turn off the virus detector. And finally, I'll show you how to do analysis of the detector to prove that it's resilient to any combination of obfuscations. So before I get into the technical details, let me just step back and put the big picture slide on. I have a friend in Wisconsin who actually finished last year. At every security talk asks, how does this technique make the world a better place? So that's this slide here. So right now, basically, for every variant, there's one signature, which means that the detectors are always behind. They're always reactive, and they cannot detect. They have no forward detection capabilities. What I would like to do with these malspecs, with the specification of malicious behavior, is able to catch many variants, all related to each other in some sense. Ideally, a specification would describe a high-level behavior, such as mass mailing worm, and stop all those worms. Yeah.
My understanding is, in practice, false positives are much more important than a false negative issue. Are you going to talk about false positives at all?
I will mention it. So my implementation errs on the side of being incomplete. So I have no false positives, but I certainly have false negatives.
So you will not catch any behavior that is shared by malware and good software.
That's correct.
Okay.
So related to this, just to mention, the problem in the end is undecidable. So I'm not claiming that I solved the malware problem once and for all. I'm just raising the bar and making it harder for malware writers to create new malware. So malware detection in this setting comes down to 4 questions. First, how do we specify behavior? Then how do we detect it efficiently? How we extract the specification automatically, because in many cases specifying behavior or specifying software in general is tedious. And finally, how do we prove that the detector and in general the detection algorithm is sound or complete or both. And today I'm going to talk about these 3 topics. If you're interested in the question of mining behavior automatically from malicious code, I'll be happy to talk to you about it after the presentation. So we have a range of choices for specifying behavior. At one end, we have byte signatures. We know those do not work very well because they're too specific, too narrow for the task. At the other end, if we take an English level description and try to enforce it, that's as close as it gets to the semantic level we would like to achieve. But in the end, the detector is very slow, and it's certainly not a practical system. So what I'm going to try to find is a balance between the two. I'm going to allow some syntactic elements into the specification that have to be matched exactly, and then I'll try to make the specification as generic as possible using semantic descriptions that relate these elements. I'll give an example on the next slide, actually. For now, let me say that syntactic elements mean a combination of low-level instructions, library calls, and system calls, anything in between. I'm not fixing a particular interface in the system which I'm detecting. The key issue is that the syntactic elements must be necessary for the malware to achieve its goal. If it doesn't help towards the particular goal, it's not necessary. Okay, so here's the example. About 20 lines of assembly code. This is the beginning of the routine for mass mailing in netski.b. Netski.b appeared probably about 3 years ago. It had about 50 variants or so. Don't expect you to read this assembly code. What's important here is that the malware first calls connect to a remote server and then starts executing the SMTP protocol for sending email. So those 2 components are necessary for self-propagation by email. The malware must connect to a remote server and send email. Obviously, this is not enough. There are many programs that connect to the network and send data over the network. So what I'm going to add, oops. Sorry. What I'm going to add is extra constraints on those calls. So I'm going to specify here that the connect and the send are related by the fact that they use the same socket. And this is the first constraint, that argument 1 of connect and argument 1 of send are the same. And the second constraint is that the second argument of send, the buffer that is sent over the network, is indeed part of the email protocol. This is the first command in the SMTP protocol called extended hello. In some way, another way to look at it is that this syntactic element describes ordering constraints. It specifies which operations must be performed by the malware and in what order. And the semantic components describe constraints on their arguments, the arguments of those operations, and also implicitly they define ordering constraints between the operations. If we were to build a full malspec for mass-mailing worm, there are really two conceptual parts. First, the malware has to send email. The standard email protocol implementation, Outlook or Thunderbird or any email client out there will have code that performs this the same way. And this is opening a socket, sending commands part of the SMTP protocol, and sending in the end the body of the email. The second part that's specific to the malicious code is that the fact that it reads from its own file and creates a copy of that file and sends it over the network. And this is simply getting the file, reading the data from the file, and then representing it in the right format for network transmission and sending it over the network. So the last two steps, reading from the file and the sending over the network, must be connected because the data from one is used in the other. And furthermore, I added a constraint there that the data that is read from the file is indeed sent over the network in base 64 encoding. This is specific to the email protocol. This is how attachments get sent. And this is the format in which the data will be, we expect the data to appear in. So for example, email client, an FTP client wouldn't match the specification because it doesn't execute SMTP commands, and the data that is sent over the network is not encoded in base 64 format. So here's a very simple version of a propagation by email malspec. We have all the operations that the malware has to execute and the dependencies between them and on the arguments. Formally, this is an AND/OR graph that lets me represent both operations that are necessary and alternatives to those particular operations. You can think of, for example, many ways of reading from a file, not necessarily just open and read. And similarly, for sending data, you can send data one byte at a time and so on. A quick plug for the part I'm going to talk about. This is actually very recent work. These specifications, in general, are fairly tedious to write manually. That's what I've been doing for 2 years. And I finally got sick of it and decided to automate this. And the way I automate this is given a non-malicious program and a set of non-banana programs, I compare their executions and extract the core malicious part of the malware. This is what I call malspec mining. So what do the constraints encode? First, the constraints encode relations on the arguments. For a particular call, I can say that this argument must have this form, otherwise the malspec doesn't match. I can also represent constraints between multiple calls, for example, in the case where multiple operations use the same resource, such as a socket or a file descriptor and so on. A more complicated constraint relates buffers or any kind of data structures between system calls. This is a case where an operation produces some data, the data is manipulated in some arbitrary way, and then is provided as the input to another operation. So what do you get by moving from byte signatures to this? Well, this is a high-level description in the following sense. First, the execution order of these operations is not constrained beyond what is necessary, what is required by the data relations. For example, open and connect are not cannot happen in any order because their arguments do not depend on each other. Second, because I'm focusing only on operations that are necessary, any obfuscation that is applied to this must maintain these operations. So any obfuscation doesn't impact the detection capability. And third, I'm using symbolic variables, which are this X, Y, and Z, and so on, that mark arbitrary locations in memory or particular registers. Keep in mind that in most cases I have to do detection at binary level. So I'm not tying the specification to a particular memory location. So how am I going to detect this? Most of my work has been on doing the detection through static analysis. Given a file, I analyze it and figure out whether the specification is applied here, is satisfied by that binary file. You can also do a dynamic analysis. Actually, I started recently an implementation of dynamic analysis, and that has some good results as well. You can implement it as a host-based ADS, inline reference monitors, and any variation of dynamic analysis you can think of. But in the big picture, what's important is that malspecs do not depend or do not require a particular detection method. So let me first talk about, actually the rest of the talk will be mostly about the static analysis part and how to detect the specifications. The setting is fairly simple. I start with the binary file. This is the suspicious program. I do not have any information other than the bytes in the file. There is no debug information. There is no source code, no such information. And I have a specification that I want to check whether there is code in the program that satisfies it. Another way to look at it is to see whether there is a path through the program. If I look at the program as just a big graph of instructions, a control flow graph or interprocedural control flow graph actually, whether there's a path through this program that satisfies all the specification. It means two things. First, that this path has to contain all the operations that appear in the malspec, and they have to appear in the right order. And second, these operations, operations that appear in the malspec that have constraints on them, the corresponding code in the program has to satisfy those corresponding constraints. So if I look at just open and read, there's one constraint on it that the file descriptor from open is used by read. The corresponding code in the program has to satisfy the same constraint. Well, in this case, the program obviously doesn't use symbolic variables, using actually particular memory locations or registers. So the constraint in the program is expressed in terms of the register that corresponds to the symbolic variable Z in this case.
So don't you kind of have the holding problem here?
Yes, very much so.
Okay. So you're going to tell me about how to deal with it.
I'll get it.
Well, the question was, isn't this the halting problem? And the answer is yes. So now we're going to hear it. Okay.
I'm not solving the halting problem. Just for that.
I hope not.
Yeah, I have a very quick solution.
I wouldn't believe it if you said it.
So another way to look at this constraint, specifically in the case of equality between arguments, is to say that the program code that's highlighted here between the two operations is a semantic knob with respect to that register or variable. Basically, it doesn't change the register or variable. So a very simple solution. I'm going to talk about two solutions to this problem. A very simple solution is to enumerate code sequences that preserve particular expressions and then basically do a simple pattern matching. Take this code, compare it with a large list of code sequences and see whether it matches. So I actually implemented this first version. The program goes through a disassembler. I construct the control flow graph. I perform the graph matching to identify the operations that are interesting from the malspec point of view. And I check the code, whether the code sequences between the matched operations are or appear in the database of known semantic knobs. And if they all appear in there, then I'm done. It means the program is malicious with respect to that sequence. To test this system, I took known malware, known instances. Is there a question?
Question. On this previous page, I mean, I have not done interprocedural control flow analysis myself, but I've heard it's hard even when you're just working against the commercial compilers. And it seems that kind of invoking an adversary as the generator of your code makes it sound. I mean, why should we expect it to be hard to obfuscate the actual control flow, or should we expect it to be easy to obfuscate the actual control flow? What should be our expectation there?
There are actually many techniques for obfuscating the control flow. So recovering the control flow graph is non-trivial. Right now, they don't. The malware writers don't use those techniques. It's certainly possible to do that. I mean, there are, I think, commercial tools for obfuscation, for intellectual property protection, that will effectively destroy the control flow of the original program and make it almost impossible to analyze. For now, I'm assuming that I can recover it to a large extent, or enough to be able to find the malicious sequence in there. Yes.
Related question: how do you deal with packed malware? Because I'm assuming if you're using any significant sample set, you're going to encounter at least a few.
Right. Actually, nowadays most malware, at least 60% of malware supposedly is packed, and most samples I see are actually packed. For packing, I have a dynamic analysis that solves that problem. Basically, I run the malware in a contained environment and stop execution as soon as the packed code, the unpacked code gets control. And at that point, I have all the code I need to analyze. So,
When you just run it and look for dynamic patterns, right? I mean, the things you were showing, they were system calls.
Right.
It's easy to instrument the system call interface. Doesn't matter what they do. Can you just run it?
You can do that, certainly. So the
premise was that you could run the thing in a constrained environment in a VM or something that's not going to.
Right. The question is whether the malware will actually exhibit the malicious behavior in the constrained environment. So what happens is most cases is that the packer is applied to the malware to the malicious program after the malicious program is written fully. So the packing happens in all environments in most cases. What happens after packing is that the malware often checks for particular conditions to make sure that it's not running in a virtual machine, for example, or it's running only between certain dates and so on. So it might be that if I do dynamic analysis, I might not see the malicious behavior in that particular execution. This being said, I have some numbers I'll show you later on about dynamic detection and how it works in many cases. So comparing this simple implementation with bisignatures, for this I just obfuscated known variants using toolkits of the web and testing against commercial antivirus and my implementation, which I called safe. In this case, the results were good. Commercial antivirus wouldn't be able to detect any of the obfuscated variants. Fundamentally, it comes down to the fact that commercial antiviruses will catch only things that they have seen before. So what I did for all this infrastructure, basically, I moved the pattern matching. Yes.
Can you go back one slide? All this malware are like a worm or like
Which sort of viruses?
Trojan horse? What, sir?
These are viruses.
Only viruses.
Yes.
Okay. I heard for spyware, those antivirus vendors may apply some behavior-based detection, right?
It's certainly possible. I haven't looked at spyware detection.
Is there any difference between spyware and virus?
They're harder to detect in the sense that most spyware just acts as a good program that leaks information. So it doesn't destroy the integrity of your system or the integrity of the network in some sense. It just leaks information. So it violates your privacy, which is harder to detect in general, unless you do complete information flow tracking at the OS level.
I guess it's all up to the user. And certain spywares, they are actually malware.
Right.
They're actually really doing bad things. They're really not supposed to do. Certain malwares, to some people, they're fine. To some people, they consider them
Right. I guess what I'm saying is that the specification language that I mentioned here might not be very well suited for spyware, but it can certainly describe, violation of safety properties in general.
because certain categories of spyware have the same behavior as the good programs. Then detecting the spyware would have false positives.
Right. I mean, it depends what defines as spyware. There are browser toolbars, and depends who you ask, they'll say that, well, this browser toolbar monitors my behavior, and that's bad, or it's good because it provides me extra features. So.
I guess it's related to that. I'm still worried about the false positive question. How can you be sure? 100% looks good, but how can you be sure that you've tested a large enough universe of, you've kind of projected out the set of good software that might be related to this, but how can you be sure that you've tested a large enough universe of good software? You have to be absolutely sure that everything you're doing here and everything you detect is actionably bad, that there's no possibility that anything good would fall into your grasp here. How do you verify that?
Through lots and lots of testing. So the testing I did is basically testing against a large number of binaries from standard Windows installation.
How large?
2,000.
2,000 is.
Yeah, this is not. I don't have enough of a large enough collection to test against. I'll get to that.
Did you do the obfuscation? Is that your obfuscation, or is these obfuscated malware in the wild?
I started with malware in the wild. I took obfuscation toolkits that you can find on the web and applied those. So I only applied the tool to the malware. I didn't actually write the obfuscation myself.
Those variants may not even exist in the wild, so your commercial AV, if they're based on signature, should not catch them, right?
Right.
Yeah.
Which commercial AVs?
Yes. Did you try Microsoft?
This was test from 3 years ago, so I didn't have the. So I tested against McAfee, Symantec, and Command Antivirus. This is what we had available in the department at the point, and I actually don't know who makes Command Antivirus.
Okay, I have a question. Did you have one mail spec for these 4 viruses, or you have for each of them you have one mail?
I had one specification for each.
One specification for each.
Right. If we move on, I'll show you how to write the specification for multiple malware.
How many different obfuscation toolkits did you use?
There are 2 obfuscation toolkits. The obfuscations were related to inserting junk code and reordering the code. Reordering code. In the back.
Me?
Sorry.
This test, will you have additional results? I know recently there's been some postings from AV Comparatives that goes through quite a number of different types of AV products as well as AV threats. Have you been able to test against those databases?
I haven't followed up on those tests. These are tests from a couple years ago, and I focused after this initial work. I focused more on improving the detection, basically such that I can write one specification for many malware.
The behavior analysis is great technology, but what you describe, and actually what you say, such an antivirus that use only binary sequence matching, that about 15 years ago. So now, for instance, what you described, Symantec uses this behavior analysis for detecting code red. Basically, it penetrates the computer or the host, then it tries to send itself. That's how they detect no signature. So then they have the email worm capability. Then there is the IBM digital news system and behavior analysis system. So actually the first question is, what new are you proposing? Second question is, from the behavior analysis that you proposed, also good, but from my experience, they're about 10% of FPs.
They're 10%, sorry?
FPs, false positives.
False positive.
So, and then how do you deal with real obfuscator that put up some extra instructions, like that does nothing, and then probably will confuse your pattern? What is it?
I cannot comment on the technology that Suntech has. I haven't tested it, and I don't have the information to comment on that. To handle additional obfuscations, actually, if you let me move on, I'll address that question. There's a question back there.
So it seems like one of the questions around what do you do with obfuscation? In your paper, you said that the thing that makes your obfuscation or that makes your detector more robust is the fact that you're looking for instructions and sequences that have the same effect on memory. And it seems to me then that the way you raise the bar so that the attacker can't just modify the code, but now all you have to do is modify the output of the code. Right? If the thing that if you're looking at the unpacker, you can just modify the unpacker to emit some no-ops, and now the memory doesn't look the same on the output side. Even if the instruction trace involves some no-ops now.
I'm not sure I understand the question exactly.
Well, perhaps I'll be able to ask it again when you...
Well, let me present the other technique, and then maybe we can ask again, or we can take this offline. Okay, so there are a couple benefits to this. By moving basically to pattern matching across the control flow graph, I gain control flow sensitivity, fundamentally. And because I use symbolic variables, I don't depend on particular memory locations. The last piece, the fact that I have a database of code sequences that are all semantic no-ops are, is certainly slightly better than byte signatures, but it's also a fundamental limitation. Because basically, the malware writer has to come up with a sequence that doesn't appear in the database and will evade detection. So going back to the original problem, which feels a lot like the program verification problem, is we have a code sequence that I want to verify a certain property about. We have a program constraint that came from a malspec, and I have a code sequence that I want to verify on. And what I really like from a detection point of view is just to have a black box, some magic oracle that I can just ask queries and get the results back and not worry about anything else. Unfortunately, this is exactly the program verification problem. It's undecidable, and there's no perfect solution. But there's been lots of work in the last couple of years on improving, on building better tools for program verification. This is based on the advances in set solvers. Set solvers became faster. They support larger formulas that you can build on those. You can build tools that can handle richer logics. And bottom model checking, for example, has really taken advantage of this. So what I'm going to do is take the set solvers, use them as decision procedures in my case, and basically benefit from all these advances. Keep in mind that these decision procedures are just an approximation for a complete oracle. Yes.
What's a set solver?
Oh, sorry. Set solver is a solver for checking whether a logical formula is satisfiable. So you have a logic formula, and you try to determine whether there is an assignment to its variables such that it holds true. In simple case, the problem is exponential. You have to try all combinations. Yes.
Are sat solvers hard for an adversary to defeat?
To what?
Defeat, to give it an input such that it just can't to take any arbitrary input and pad it so that it's hard to analyze?
I'm not sure what hard to analyze means. So in some sense, this opens an algorithmic attack. It's possible to build a malware such that the set solver takes a long time to solve the question.
So that's exactly the attack John is talking about. What if a malware denial of service the set solver?
I asked, is that hard? Is it hard to DOS the sat solver?
Okay.
This is how much are you raising the bar for the adversary if this is now what he has to do? DOS your sat solver.
Well, I don't know exactly how smart the adversary is. If they're all, PhDs in program verification, probably they can, whip up something in 10 minutes.
They've never heard of SAT, and they're just learning about software engineering.
Okay. I don't know. We should go arrest some of them and ask them.
Listen.
Okay, that's true.
They sound like they're really proud that they discovered software engineering last year. So, yes, in theory they haven't gone to yet.
So the way this is going to work is I'm going to take the program, convert it to a formula that basically represents the code sequence as a straight state transfer function, and then ask the question whether that formula that represents the program satisfies the constraints in the program. In action, here's an example. Actually, I'm not going to walk through this, but just to give you a flavor, starting from the assembly code, you can represent what the assembly instructions do as logical formulas over the program state. In the actual implementation, I'm going to scrap the pattern database and just replace it with the constraint satisfaction solver. In my implementation, I use two tools. One is a theorem prover called Simplify. The other one is a boundary model checker called Euclid. And using this, here I changed the testing strategy. Instead of doing manual obfuscation with basically generating new malware each time, I wrote a specification from an early version of Netscape. And based on this, I used the specification to test later versions of Netscape. So in this case, the attacker controls the generation of variants. I don't insert my own variants. All of them were detected by virus scanners, but each requires separate signatures. In my case, using one specification, I was able to detect the whole set of Netscape variants. Similar results for Beagle. What this shows effectively is that if you generate a specification from a new malware that you see now, you can detect variants that might appear later in the family. This is what I call forward detection. Quick change of topic. So up to now I talked about static detection, static analysis. These are some recent results from the dynamic analysis implementation. This is where the malware is run in the contained environment. We trace the execution at all levels, so instructions, libraries, calls, system calls. And with a couple of mousepecs, we were able to detect, with actually 8 mousepecs, we were able to detect 300 variants across multiple families, different generations from different years and so on. It shows that the same specification really can catch malware from different authors. Okay, back to static analysis. What I've shown is that by replacing the database of patterns with decision procedures, I can handle a lot more the obfuscations that are present out there, and can handle even arbitrary code modification and code evolution. If the attacker just inserts, let's say, error checking into the code without modifying anything else, it's not really junk code, but I can still detect that this is equivalent to the original code. The downside is that decision procedures are slow, and we're talking about taking 5 to 15 minutes to detect a program that has 20,000 instructions, so 40K of binary code. On the other hand, the simple pattern matching that I showed earlier is very fast, under a second or around a couple of seconds, while commercial virus scanners take below a second per file. So obviously the time is a key component here. So what I'm going to do is use the chip detector, the safe approach, where I check just the pattern of code in a database. And if that fails, I move only to the more expensive detector at that point, with the hope that a lot of the code will be caught early on. Yes.
Does it mean that clean files will scan for longer than infected?
I didn't hear the question.
You said that if expensive, can you go back?
Chief decision procedure fails to provide an answer. He's asking, can it err in both directions? Like, does the chief decision procedure ever say definitely clean?
Right.
Well, no, by design you can make the decision procedure, the cheap ones, such a way that they don't. You're saying if it makes mistakes, in the sense that it will say yes when it's actually not infected.
Right. If the file is clean and we apply all sorts of techniques and finally we realize it's clean, we apply 10 sort of detections instead of infected file. The first one matched, so clean. Infected. It means probably if my computer is not infected, the scanner will spend for scanning like days. Right?
Right.
Okay.
We can take this offline. So I'm going to add one more decision procedure to bridge the gap between the two. So the first one, the top one ran in a couple of seconds, the bottom one's ran in minutes. In the middle, I'll have a decision procedure that can tell me whether a piece of code doesn't satisfy a constraint. And this is simply by running the code on random inputs and figuring out whether at the end whether the state after the execution satisfies the constraint. If it doesn't satisfy the constraint, it means that I found one path for the program that doesn't satisfy that fails the constraint, and I can just throw away that code. I don't need to go to more expensive decision procedures for that. And with this, the detection works in the following way. I take the program fragment that I want to check on the constraint, query it for the first decision procedure. If that passes, then I'm done. If not, I need to go to the next one, and so on, working through the stack until I reach the bottom decision procedure, which is basically I have to take its answer for being correct. The end result is that the detection, if you look at the middle column, the average detection drops from 10 minutes to about a minute to a minute and a half. It's still certainly slower than commercial virus scanners that detect in under a second, but there's a trade-off, I guess, between detection power and cost.
So, yes. Let's see if I can restate the question that I think we got from the back. So what you've done here is something that will quickly pick off a lot of known variants and get to a yes, this is bad really quickly. Most of the time, I hope, the things I run on my computer are not malware. Are those things always going to go through the long thing so that before I can start any application or write any file in the file system, I have to wait 15 minutes?
Most of them might be eliminated by this random execution sequence. They'll basically say that this is not malicious because there's one path, for example, that is not malicious in between those operations. So they'll get eliminated quickly.
So if I were to want to attack that, then all I need to do is come up with a probabilistic piece of malware, right? One that 1 time out of 3 does something bad, 2 times out of 3 it prints hello world or exits or something. Right? That's like an easy thing to attack.
Right. So it means that your piece of malware then will have to go through the whole stack and it'll be slower to detect. I assume that the people who write good software are not trying to make to take longer to be detected as clean.
No. What I'm saying is maybe I misunderstood what you said. You told me that if the random detector thing ever finds an execution path through that doesn't do anything bad, then it'll pass the software off as not. That's a point of attack, right? So if I'm a bad guy, and the way the rules of this game work is your thing gets published and it's out there, and then the bad guys get to design an attack against it.
Right.
So if I'm a bad guy and I know that your thing works that way, I produce a piece of malware that's only bad 1 time out of 3. The other 2 times, it's completely benign. And the whole point of doing that is that then it's going to trick your random detector and get passed through. Does that make sense? Or am I completely mistaken?
I think you're correct. I'll have to. Sorry? Yes, absolutely.
Right, and that's a point of attack. I mean, you won't see it in extant malware because they haven't had the opportunity to read your paper and actually.
Right. Yeah, that's why I mentioned initially that I have false negatives. I don't detect all malware in a particular family. Right.
That's one thing. Another thing is that if there's something that, as a bad guy, I can design it to regularly produce false negatives, then you fall over. Right? Because, you're not dealing with random things. You're dealing with an adversary who may or may not understand SAT, but sure as heck understands random execution and false negatives.
Right. So one way to handle this is to remove the randomness from that stack, in which case the scanning becomes much slower, but at least conceptually scanning benign programs has to happen only once per program, right? For example, when you install it, you scan it, you remember somewhere that it's been scanned. For example, you could sign the file and say it's scanned, and you're done with it.
At that point, it's still going to be. Those cost numbers you said were for 40K of code.
Yes.
Okay. Many things are bigger than that, and I'm guessing that time isn't linear in the code size. Why not?
Yes.
It takes me 6 days to install. Anyway, okay.
I think there are operational ways to handle this, for example, in an enterprise and so on. So, yes.
So, first of all, I'd like to point out that you have to pretty much rescan each file every time, because the approach of keeping a database of files and checking each file every time you start to against the database was really used like 10 years ago, and then they dropped it, presumably because it doesn't work. All malware of the time just start by deleting all the databases they can find on the hard drive and then just move on. So this would have to be applied on each file that is touched. And second of all, I just do these times include the time that IDA-Pro takes to disassemble a file? Because on average that's around 10 to 20 seconds.
No, it's another 20 seconds for that. In general, IDA-Pro probably is not, in my experience, not the most efficient disassembler.
It's a very good output that you can parse later on. The problem is if you don't have that output, then...
Okay, so you probably need to add another 20 seconds to this time. So, order of a couple of minutes. To the point about databases, the key is that there has to be something on the system that you can trust. So, if the whole system is completely broken and you cannot trust, let's say, the kernel or anything like that, then you cannot make any guarantees at that point, right? So I'm assuming that you can have a database where you can either the database of files, or you can sign the files and protect the key itself. Protecting, let's say, a key in the kernel might be easier than protecting the database. So there has to be something in the system that you can trust. At least in the simplest case, the virus scanner has to be protected. Otherwise, somebody can just operate the code to always say not infected, and that's it.
Most virus scanners operate under the assumption that they can't trust anything, pretty much. I mean, really, every time you have a rootkit, right, you're supposed to detect rootkits, and yet you cannot trust the system to show you what it's actually doing, right? I mean,
so how do you enforce that the virus scanner is not modified itself?
You cannot enforce that.
So then all virus scanners are broken?
No, they're not broken. The design. So first of all, virus scanner usually operate under the assumption that, look, I'm going to deal with the things that I've seen out there as quick as I can and as best I can. But that's it. I mean, once a system isn't trusted again, you cannot trust anything it does. But the point is, if you can only operate on a system you can trust, then there is little reason to have a security solution, right?
No, I'm not saying to trust the whole system. You only have to trust some small part of it. At least you have to assume, let's say, that the part that catches files before they run works, right? Before being able to hook into the OS such that you can catch execution of new files. Maybe we can take that offline. So. Yes.
High-level question: are you interested in defending only against current obfuscation techniques or future ones, in particular ones that are done after your work and after they see what your techniques are?
So there are two parts to this question, I guess. First, in the current implementation handles current obfuscation techniques. And then I have some theoretical work that shows that this can be extended to handle all obfuscation strings in a particular class without updating the virus detector every time.
Okay, but you're not concerned with blocking off all means of obfuscation. You're just dealing with stupid attackers, relatively stupid attackers.
Right. I'm not sure, practically speaking, I'm not sure it's possible to detect all obfuscations on a particular program. Okay, so let me talk about quickly about detector analysis. I'll go very fast since we're over time here. So what I've shown you up to now were testing results. I took the prototype, I implemented it, I tested on some files, and I got some answers. What this doesn't show is whether the detector will handle, let's say, the same obfuscation applied 3 times or 5 times, or any multiple of that. One way to do this would be to take the detection algorithm and take each obfuscation in turn and try to prove that it can handle all applications of the obfuscation. In general, this is it might be tedious, but it's doable. You have to do this for each combination. The problem it comes in when somebody comes up with a better detection technique, either static or dynamic. This is just one example. Well, then you have to repeat the work in order to determine whether the detector can handle the obfuscation or not. In the end, this is really very tedious and time-consuming, just to determine whether the detector handles a class of obfuscations. So one way to establish this is to describe both detectors and obfuscators in the same language. This is not a trivial task because the obfuscations are often described in terms of transformations over byte sequences or simple low-level structures. Detectors can be as complex as you want them to be. Matching the two is non-trivial. Second, there are many obfuscations out there. And handling each one in turn will take forever. So let me split first resilience, obfuscation to resilience in 2 parts. First, I want to show that the detector is sound to all obfuscated variants and then complete with respect to those, meaning that it won't have false positives or false negatives. Now, if we look at just soundness, basically says that if the detector says that this is infected with a variant of the malware, then really the variant is an obfuscated version of the original malware. Or another way to look at it is to say that there is a path through the infected program and the path through the original malware, such that the 2 paths are equivalent under some formula. Well, since I don't have much time, I'm just going to basically say that path equivalence can be very nicely mapped using abstract interpretation. In which case, I apply the detector basically acts as an abstraction on the original program and the malware, and then check whether the 2 resulting abstractions match up. In which case, the program is a obfuscated variant of the malware. Another way to look at it is that if I obfuscate, well, the abstract interpretation lets me express something like this, where alpha is the abstraction that represents the detector, and effectively this says that if I can find a path in the program P that matches a path in the program in the malware M, and they look the same under this abstraction, then indeed the malware is the program is an obfuscated version of the malware. So this lets me prove about the soundness and completeness of the detector in a logical framework. And it's a uniform way to treat both obfuscation and detection. In my case, describing the detector as an abstraction is non-trivial because the detector depends on 3 pieces, those black boxes I kept describing: the disassembler, the control flow constructor, and the decision procedure. Now, if I assume that those are ideal, meaning that I can always recover the control flow graph, I can always recover all the instructions on the program, and the decision procedures are perfect, then I can basically show soundness and completeness to a large class of obfuscations, meaning that basically I'm proving relative completeness and relative soundness relative to those 3 oracles. So this is the high-level view, starting with a binary file, applying a static analysis to it to recover the control flow graph and extract all the instructions, and then use decision procedures to determine whether the specification is satisfied by the malware. And this leads to resilience to both common obfuscations and to evolution in a family and across families. Real quick, I want to mention two ideas for future work. First is hybrid detection that combines static analysis and dynamic analysis. In general, pushing static analysis further means that the cost is higher and higher, which is certainly not desirable for detection. And this is because static analysis analyzes all program paths, so it gives me a full view of the program, but is imprecise. It is necessarily imprecise. On the other hand, dynamic analysis tells me exactly how the current program execution works, but only one execution path. So combining the two means that I can use static analysis to describe parts of the program. Let's say if static analysis can decide the parts of the program are not malicious, and then at the points where the static analysis is not sure, I can automatically trigger a dynamic analysis that monitors the program and decides whether the program is malicious or not. The second idea is more long-term. I don't have a good name for it. I just call it software accountability. Ideally, what I would like to see is, given a new program, I want to be able to know what the program is going to do to my system. And after I run it, I want to be able to know exactly how to undo those effects. If I don't like what the program did, I should be able to automatically undo that. Now, the way to look at it is to take program behaviors. So a program is composed of multiple behaviors that interact with each other, and treat them as first-order objects. I want to be able to remove behaviors from a program, add new behaviors into a program, and modify those behaviors at will. I worked in a couple other areas. Most of this work fed into the malware analysis and detection. That's core part of my dissertation. I also looked at software protection and some side projects that weren't related to malware analysis. I can certainly talk to you about any of these. I think this is all I have. Thank you.